What if I told you that the universe holds secrets so bizarre, they make science fiction look ordinary? Picture a place where stars scream in silence, black holes bend time like putty, and entire galaxies vanish without a trace. This isn't the plot of a blockbuster movie, it's the reality of the cosmos we live in. Space isn't just vast, it's a theater of the utterly unexpected, where the rules of physics twist into knots and the impossible becomes routine. And today, we're diving headfirst into 30 of its most shocking mysteries, each one guaranteed to leave you questioning everything you thought you knew. Think you've got a handle on how strange space can be? Consider this: there's a planet where it rains glass sideways, whipped by winds faster than the speed of sound. Or that somewhere out there, a single teaspoon of material weighs as much as a mountain, squeezed into a neutron star's heart. These aren't exceptions, they're glimpses of a universe that thrives on defying logic. For every answer science uncovers, space tosses back a dozen new questions, each more baffling than the last. That's the thrill of it. The cosmos doesn't just challenge our understanding, it rewrites the textbook entirely. So why stick around? Because what you're about to discover isn't just trivia, it's a front row seat to the grandest, most mind-bending show in existence. From stars that shouldn't exist to cosmic ghosts haunting the void, these 30 facts will reshape how you see the night sky. Whether you're a seasoned space enthusiast or just curious about the weirdness beyond our atmosphere, this journey will leave you awestruck, wondering what else is out there, waiting to shock us next. Ready to have your reality rocked? Let's begin. Here's something that might catch you off guard: the moon isn't just hanging there in the sky, unchanging and eternal. It's actually slipping away from us, bit by bit, every single year. Right now, it's moving about 3.8 centimeters farther from Earth, thanks to the push and pull of tides. Imagine it like a cosmic game of tug-of-war. Earth's gravity locks onto the moon, but the moon's own gravitational tug raises ocean tides on our planet. Those tides don't just rise and fall, they create a tiny bit of friction against Earth's rotation, slowing us down ever so slightly, and like a figure skater extending their arms to slow a spin, that lost energy gets transferred to the moon, nudging it into a higher orbit. Now 3.8 centimeters might not sound like much, but over millions of years, it adds up in a big way. Picture this: if we could fast forward billions of years into the future, the moon would look smaller in the sky, and Earth's days would stretch longer as our planet's spin continues to slow. We're talking days that could last weeks, with tides so weak they barely shift the oceans. That might sound peaceful, but it's actually a problem. Tides don't just move water, they mix nutrients, shape coastlines, and even influence marine life. Without them, entire ecosystems could collapse, and here's the real kicker: this slow-motion escape isn't just happening to us. Other moons in our solar system drift away from their planets too, some much faster. But Earth and its moon, we're locked in a delicate dance that's been going on for over 4 billion years. One day, though, the music will stop. The moon will eventually reach a point where it's too far to stabilize Earth's tilt, and without it, our planet could wobble wildly, turning seasons into chaos. Luckily, we've got plenty of time before that happens, but it's a humbling reminder: even the most familiar things in the night sky are part of a story that's always changing. If you think Earth's rotation is the norm in our solar system, Venus is here to flip that idea upside down literally. While most planets spin counterclockwise when viewed from above, Venus does the exact opposite, rotating clockwise in what's called a retrograde rotation. This means if you could stand on its scorching surface, which, by the way, would melt you instantly, you'd witness a sunrise in the west and a sunset in the east. Just how weird is that? Of all the planets, Venus and Uranus are the oddballs with this backward spin, but Venus takes the cake with a day longer than its entire year. So how did Venus end up spinning the wrong way? Scientists have wrestled with this puzzle for decades. One leading theory suggests a colossal collision billions of years ago. similar to the impact that might have created Earth's moon. A smash with another planet-sized object could have sent Venus into a dizzying reversal, flipping its rotation entirely. Others argue it wasn't a single crash but a slow gravitational tug of war with the sun's intense pull, combined with its thick, soupy atmosphere dragging on the planet's surface like an anchor. Over eons, these forces might have gradually slowed Venus down, then spun it backward like a top losing momentum, but the strangeness doesn't stop there. This backward rotation plays a huge role in Venus's nightmare climate. Its leisurely spin taking 243 Earth days to complete one rotation combined with an atmosphere 90 times thicker than ours creates a runaway greenhouse effect. The planet's surface cooks at nearly 900 degrees Fahrenheit, hot enough to melt lead, while sulfuric acid rains from its toxic clouds, and because Venus spins so slowly, its day-night cycle does little to distribute heat, leaving one side broiling under endless sunlight for months. It's a stark reminder in space, even the smallest quirks like which way a planet spins can trigger consequences that turn a world into a hellscape. Here's a reality check straight from the astronauts who have been there. Space isn't just quiet, it's utterly, absolutely silent. Those epic sci-fi battles with roaring engines and exploding stars, pure Hollywood magic. The truth is, in the vacuum of space, there's no air, no molecules, nothing to carry sound waves at all. When Neil Armstrong took his first steps on the moon, viewers back home heard his famous words, but only because his microphone transmitted them through radio waves. If you'd been standing beside him without a spacesuit, you wouldn't have heard a thing, not even your own scream. The Apollo missions proved this in the most eerie way possible. During moonwalks, astronauts communicated via their helmets, but the moment they turned off their mics, the silence was overwhelming. No wind, no rustling, not even the faintest hum, just pure, unbroken stillness. Even catastrophic events like supernovas or colliding galaxies unleash unimaginable energy, but without a medium to vibrate, those explosions would play out in perfect silence to any nearby observer. Why does this happen? Sound needs something to travel through, whether it's air, water, or solid ground. On Earth, air molecules bump into each other, creating waves our ears pick up. But space is a near-perfect vacuum, with particles so sparse they might as well be invisible. That's why astronauts rely entirely on radio transmissions. It's the only way sound can travel out there. This silence isn't just a curiosity, it reshapes how we explore. Spacecraft designers don't worry about aerodynamics for sound, they focus on vibrations that travel through the ship's structure. And for future Mars colonists, the red planet's thin atmosphere might carry faint noises, but most of their world will be as quiet as a tomb. It's a haunting thought. The universe teems with motion and violence, yet it all unfolds in a silence so deep, it defies human intuition. Time works differently on Venus, so differently that if you lived there, you'd celebrate your birthday before your first full day was over. While Venus takes just 225 Earth days to complete one lap around the Sun, it spins so sluggishly that a single rotation on its axis lasts 243 Earth days. That means a Venusian day is actually longer than its entire year. Imagine watching the sun crawl across the sky for months, only for it to finally set and reveal a night that lasts just as long. What causes this cosmic time warp? Blame Venus's thick, choking atmosphere, a dense blanket of carbon dioxide with clouds of sulfuric acid. This atmosphere isn't just toxic, it's heavy, weighing down on the planet's surface with 90 times the pressure of Earth's air. Like a spoon stirring molasses, this soupy atmosphere creates immense drag, resisting the planet's spin and slowing it to a crawl. Some scientists think Venus might have spun faster in its youth, but over billions of years, the sun's gravitational pull paired with atmospheric friction acted like a cosmic brake, gradually stealing its momentum. Here's where it gets even weirder. Because Venus rotates backward, its slow spin combines with its orbit in unexpected ways. If you could stand on its surface and survive the 900-degree heat, you'd witness a sun that rises in the west, take 117 Earth days to reach noon, then another 117 to set in the east. And thanks to that backward rotation, a full solar day from one sunrise to the next is just 116.8 Earth days. That's shorter than its sidereal day because the planet's retrograde spin works against its orbit. Wrap your head around that. Timekeeping on Venus isn't just slow, it's fundamentally broken by the planet's own contradictions. This extreme environment makes Venus a laboratory for chaos. Its sluggish rotation means one side bakes under relentless sunlight for months, while the other plunges into prolonged darkness, yet the thick atmosphere spreads heat so efficiently that there's barely any temperature difference between day and night. Even time itself seems to lose meaning there, while Earth's steady rhythm of days and years shapes everything from biology to culture. Venus reminds us that the universe plays by its own rules, and sometimes those rules defy all logic. Deep in the cosmos, 12 billion light-years from Earth, floats a discovery so staggering it rewrites what we thought possible: a cloud of water vapor containing 140 trillion times all the water in Earth's oceans combined. To put that into perspective, if you gathered every drop from our seas, lakes, and glaciers, multiplied it by 140 trillion, you still only match the sheer volume of this single cosmic reservoir. This isn't just a puddle in space, it's an ocean without shores, drifting near a supermassive black hole in the heart of an ancient quasar, a relic from when the universe was barely 1.6 billion years old. How does something so vast exist so early in cosmic history? Water, it turns out, isn't just an earthly luxury, it's been part of the universe's recipe since nearly the beginning. This cloud, spotted by astronomers using the Z-spec instrument at the Caltech Submillimeter Observatory, suggests water was abundant even when the cosmos was in its infancy. The water molecules likely formed in the turbulent environment around the quasar, where intense heat and radiation ripped apart other compounds, allowing oxygen and hydrogen to bond. But here's the twist: this cloud shouldn't be this massive. Current models assumed water took billions of years to accumulate in such quantities, yet this reservoir defies those timelines, proving the universe got a head start on hydration. What does this mean for the story of life? If water was already widespread when galaxies were young, the ingredients for habitable worlds may have been sprinkled across the cosmos far earlier than we imagined. Imagine distant planets orbiting stars in that ancient era, bathed in water-rich nebulae, potential cradles for life in an era when Earth didn't even exist. It's a humbling thought. The very substance that fills our glasses might have been brewing in space before our solar system was a twinkle in the Milky Way's eye. But this cloud isn't just a relic, it's a clue. By studying its composition, scientists can unravel how water spread through the early universe, seeding galaxies with the building blocks for oceans, atmospheres, and perhaps even biology. And while this reservoir is too distant and diffuse to ever quench a human thirst, its existence reminds us that water, the essence of life, is woven into the fabric of the cosmos itself. The universe didn't just make water, it made oceans of it, long before Earth had a chance to join the party. Neutron stars are the universe's ultimate cosmic lighthouses, spinning faster than a kitchen blender and beaming radiation across the galaxy with precision that would put any human-made machine to shame. Born from the explosive deaths of massive stars, these bizarre objects pack more mass than our entire sun into a sphere no wider than a city. To grasp just how dense that is, picture this: a single sugar cube's worth of neutron star material would weigh as much as Mount Everest, crushed down into something you could balance on a spoon. That's not just heavy, it's matter pushed to the brink of oblivion, where atoms collapse into a sea of pure neutrons so tightly packed, they defy the laws of everyday physics. What makes these stars truly surreal is their dizzying spin. After a supernova explosion, the surviving core, now a neutron star, conserves the original star's angular momentum, but shrinks to a fraction of its size, like an ice skater pulling their arms in to spin faster. The result, some neutron stars rotate hundreds of times per second, their surfaces whipping around at nearly a quarter the speed of light. As they spin, their intense magnetic fields funnel radiation into narrow beams that sweep across space like a lighthouse's flash. If one of these beams happens to point toward Earth, we detect it as a pulsar, a celestial metronome ticking with such regularity, it rivals atomic clocks. But the strangeness doesn't stop there. The magnetic fields around neutron stars are so powerful, they'd rip the electrons off your atoms from thousands of miles away. Some, called magnetars, take this to the extreme. Their magnetic fields are 1,000 trillion times stronger than Earth's, capable of warping the very shape of atoms. And when these stars crack under the strain, they release starquakes that send shockwaves through space-time, lighting up the cosmos with bursts of gamma rays. Yet for all their violence, neutron stars are also cosmic alchemists. The crushing pressures inside them forge elements like gold and platinum, scattering these precious metals into space when they collide, seeding future generations of stars and planets. They're reminders that even in death, stars don't just vanish, they transform, leaving behind objects so extreme, they stretch our understanding of reality itself. There's something out there in the cosmos, a gravitational monster so powerful it's tugging entire galaxies, including our own, toward it at over 14 million miles per hour. Astronomers call it the Great Attractor, and it's one of the universe's most baffling mysteries, hidden behind the Milky Way's dense band of stars and dust, an area known as the Zone of Avoidance. This invisible force warps the motion of thousands of galaxies, bending their paths like a cosmic magnet. Despite decades of searching, we still don't know exactly what it is, only that it's massive enough to rewrite the rules of our local universe. The story begins in the 1970s, when astronomers noticed something odd. Galaxies in our corner of space weren't just drifting apart from the Big Bang's expansion, they were also streaming toward a specific point in the constellation Centaurus. This motion, dubbed dark flow, suggested an unseen concentration of mass lurking about 250 million light-years away, pulling everything toward it with irresistible gravity. But when scientists pointed their telescopes in that direction, they hit a wall literally. The Milky Way's central bulge, thick with gas and dust, blocks our view like a cosmic blindfold, leaving the Great Attractor shrouded in mystery. So what could be yanking galaxies with such force? One leading theory points to the Norma cluster, a dense gathering of galaxies sitting near the suspected epicenter. But here's the catch, even its combined mass isn't nearly enough to explain the pull. That's led researchers to suspect something far grander, like the Laniakea supercluster, a sprawling web of galaxies spanning 500 million light-years, with the Great Attractor as its gravitational heart. Imagine it as a cosmic watershed, where galaxies flow like rivers toward a hidden valley of mass, yet the plot thickens. Some observations suggest the Great Attractor might not be the final destination. It could itself be pulled by something even larger, like the Shapley supercluster, a titanic structure 800 million light-years away. This raises a spine-tingling possibility. Our universe's gravity might be far more lumpy and unbalanced than we thought, with vast invisible structures sculpting the motion of everything around them. Until we peer behind the Milky Way's veil, the Great Attractor remains a cosmic siren, luring us deeper into the unknown. Jupiter's Great Red Spot isn't just a storm, it's a planetary titan, a swirling maelstrom that's raged for at least 400 years, possibly longer. Imagine a hurricane so vast it could swallow Earth whole, with winds screaming at 430 miles per hour, fast enough to shred steel. This crimson vortex, twice as wide as our entire planet, isn't just enduring, it's evolving, shrinking mysteriously while refusing to die. Astronomers first spotted it in the 1600s, when telescopes were still a novelty, and it's outlasted every human empire since. But what keeps this ancient tempest churning, and why is it slowly fading? The storm's secret lies in Jupiter's chaotic atmosphere, a layered cocktail of hydrogen, helium, and neon, striped with jet streams that act like celestial conveyor belts. Unlike Earth's hurricanes, fueled by warm ocean water, the Great Red Spot is a high-pressure system, an atmospheric eddy trapped between these raging winds. It spins counterclockwise like a gargantuan wheel, dredging up material from deep below Jupiter's clouds, which reacts with sunlight to create its signature brick red hue. But here's the twist: since the 1800s, the storm has been shrinking. Once wide enough to fit 3 Earths side by side, it's now barely wider than one. Some scientists believe it could vanish within our lifetimes, while others think it might stabilize, a permanent scar on Jupiter's face. What's causing this slow-motion collapse? Turbulence at the storm's edges seems to be peeling it apart, as smaller vortices chip away at its energy. Yet, despite losing ground, the Great Red Spot isn't going quietly. Recent observations show it's growing taller as it narrows, stretching deeper into Jupiter's atmosphere like a sinking ship raising its mast. This vertical extension might be its survival strategy, tapping into hidden energy reserves beneath the cloud tops. And there's another puzzle: the spot isn't just shrinking, it's changing color. Once a deep crimson, it's now often more of a pale orange, possibly due to shifts in atmospheric chemistry or altered sunlight exposure. Whether it's fading for good or just entering a new phase, this storm story is far from over. It's a reminder that even in space, nothing lasts forever, but some things fight harder than others to stay alive. The Boomerang Nebula holds a record that's hard to fathom. It's the coldest natural place ever measured in the universe, chilling at a bone-shattering -272 degrees Celsius. That's just 1 degree warmer than absolute zero, the theoretical temperature where all molecular motion stops. To put that in perspective, even the vast emptiness of space between galaxies isn't this cold. It hovers around -270 degrees, warmed slightly by the faint glow of the Big Bang's leftover radiation. So how does this eerie nebula, located 5,000 light-years away, plunge temperatures lower than the cosmic baseline? The answer lies in its death throes. The Boomerang Nebula isn't just a cloud of gas, it's the final cry of a dying star, a red giant in its last act. As the star sheds its outer layers at breakneck speeds, expelling material outward at over 180,000 kilometers per hour, the gas expands so rapidly that it cools dramatically, like cosmic air conditioning cranked to the extreme. Picture a can of spray paint. When you press the nozzle, the gas inside expands and cools instantly. The Boomerang Nebula works the same way, but on a stellar scale, with enough expelled material to fill a solar system. What makes this nebula unique isn't just the expansion, it's the symmetry. Most dying stars eject material in uneven bursts, creating chaotic, lopsided nebulae. But the Boomerang's near-perfect bipolar shape, with 2 identical lobes of gas flowing outward, allows the cooling process to happen uniformly, dropping temperatures to that record-breaking low. Even more bizarre, the nebula's namesake, boomerang shape, captured in early telescope images, might be an illusion. Newer observations suggest we're seeing it edge-on, like staring at the rim of a giant hourglass, with the coldest gas concentrated in a narrow central band. But here's the real kicker: this deep freeze won't last. As the nebula continues expanding, its gas will eventually thin out enough to be warmed by interstellar radiation and the faint heat of the cosmos. For now, though, it stands as a fleeting monument to nature's ability to push extremes, a pocket of near absolute zero hiding in plain sight, a ghostly reminder that even in the vastness of space, cold has its limits. Imagine a world where the ground beneath your feet isn't rock, it's diamond, not scattered gems, but an entire planet made of crystallized carbon, glinting like a cosmic jewel. That's not science fiction, it's 55 Cancri, a planet orbiting a star 40 light-years away, and it's likely one of the most valuable objects in the galaxy. Roughly twice Earth size but 8 times as massive, This dense world is so carbon-rich, scientists believe a third of its mass could be diamond. Picture mountains of pure gemstone, seas of molten graphite, and a core that might be a single, monstrous crystal. How does a planet turn into a diamond? It starts with the right ingredients: a star system swimming in carbon, the same element that forms coal and diamonds on Earth. 55 Cancri orbits a star with far more carbon than oxygen, making it a cosmic factory for carbon-based chemistry. Under normal circumstances, planets form from silicates and metals, like Earth. But here carbon dominates. Add crushing pressure. This planet is so close to its star, its surface temperature hits 200 degrees Celsius, and you've got the perfect forge. Deep underground, carbon atoms get squeezed into diamond structures, layer by layer, over billions of years. It's nature's most extravagant pressure cooker. But here's the twist: 55 Cancri isn't just a diamond, it's a nightmare. The planet is tidally locked, meaning one side permanently faces its star, broiling under eternal daylight, while the other half freezes in endless night. The day side might host oceans of lava, while the night side could be a solid sheet of diamond, and if you tried to mine it, the gravity alone would crush you, the heat would vaporize your tools, and the diamond, harder than anything on Earth, would be nearly impossible to extract. This glittering world shatters our assumptions about planets. We used to think habitable worlds needed Earth-like compositions, but 55 Cancri proves the universe builds with more exotic blueprints. It's a reminder that out there, resources aren't just metals and water, they're diamonds, sapphires, and who knows what else. And while we'll never mine this planet, its existence hints at something profound. The cosmos doesn't just make worlds. It makes wonders. We've long thought of the moon as a silent, frozen graveyard, a place where geologic activity ceased billions of years ago, but new discoveries are shattering that assumption, revealing hints of volcanic whispers beneath its dusty surface. Recent data from lunar orbiters and seismometers left by the Apollo missions suggest that the moon might still be stirring, with molten rock lurking just beneath its crust. This isn't the dramatic lava flows of Earth's volcanoes. It's a subtler, more mysterious kind of activity, one that challenges everything we thought we knew about our closest celestial neighbor. The clues started piling up when scientists noticed strange, warm patches in infrared scans of the moon's surface. These hotspots didn't match the expected cooling patterns of an entirely dead world. Then came the moonquakes, tiny tremors detected deep underground, some too rhythmic to be explained by meteor impacts or Earth's gravitational pull, the most compelling evidence. Strange glassy beads in lunar soil samples, formed when molten rock cools instantly in the vacuum of space. These beads are geologically young, some possibly less than 100 million years old, a blink of an eye in cosmic terms. So what's fueling this hidden volcanism? The leading theory points to a partially molten layer deep in the moon's mantle, kept warm by lingering heat from its violent formation and the steady squeeze of Earth's gravity. Unlike Earth, where plate tectonics constantly recycle the crust, the moon's thick outer shell acts like a stifling blanket, trapping heat inside. Occasionally that heat finds a weak spot, a crack or fissure, and seeps upward, creating the faint, sporadic activity we're only now beginning to detect. This discovery rewrites the moon's geologic resume. Instead of a static relic, it's a world with a slow, stubborn heartbeat, one that still occasionally flexes its molten muscles. And if volcanic processes are ongoing, it raises tantalizing questions. Could there be pockets of subsurface magma today? Might future lunar colonists harness this heat for energy? The moon, it seems, isn't ready to be filed away as a dead rock just yet. It's got secrets left to spill, and they're bubbling up when we least expect them. Mars doesn't just have dust storms, it has apocalyptic, planet-engulfing tempests that can shroud the entire world in a suffocating haze for months. Unlike Earth's localized sandstorms, which rage across deserts but eventually dissipate, Martian storms go global, spiraling out of control until they've choked the skies from pole to pole. Picture a hurricane so vast it doesn't just cover Texas or the Sahara, but every continent on Earth simultaneously, with no ocean to break its fury. That's the scale of chaos Mars endures regularly, and it's not just a spectacle, it's a lethal threat to anything relying on sunlight to survive. The mechanics behind these storms are as fascinating as they are terrifying. On Earth, storms lose steam when they hit water or run into mountain ranges, but Mars has neither oceans nor significant topography to act as brakes. Instead, fine dust particles, as tiny as cigarette smoke, get lofted into the thin atmosphere, where sunlight heats them, creating wind systems that lift even more dust. It's a runaway feedback loop. The more dust rises, the more the atmosphere warms, fueling stronger winds that kick up yet more dust. Within weeks, what started as a regional gust can morph into a planet-wide shroud, blotting out the sun and turning the sky a sickly orange. This became a death sentence for NASA Opportunity rover in 2018. Designed to run on solar power, Opportunity had already defied expectations by operating for 14 years instead of its planned 90-day mission. But the storm that erupted that June was unlike anything engineers had seen. Dust blotted out 99% of the sun's light, starving the rover of power. As temperatures plummeted, Opportunity systems froze in the dark. NASA spent months sending hopeful wake-up signals, but the rover never responded. Its final message simply read, "My battery is low and it's getting dark." A heartbreaking end for a machine that had become part of our collective imagination. Yet these storms aren't just destructive, they're also mysterious. Why do some Martian dust storms fizzle out while others go global? Why do they seem to follow an 11-year cycle, loosely tied to the planet's seasons? Scientists suspect it's linked to Mars's elliptical orbit, which creates wild temperature swings, but the exact trigger remains elusive, and here's the twist: these storms might actually cool the planet long-term. While the initial dust blanket traps heat, the airborne particles eventually reflect sunlight back into space, like a planetary sunshade. It's a paradox, storms that rage fiercely but leave Mars colder in their wake. For future astronauts, these storms pose a nightmare scenario. Solar panels could fail, leaving habitats powerless. Dust clinging to spacesuits or equipment could jam machinery. Even the psychological toll of watching the sun vanish for months shouldn't be underestimated. Yet there's a silver lining. Understanding these storms could unlock Mars's climatic past. Some researchers think ancient global storms might have accelerated water loss, stripping the planet dry over eons. Others wonder if dust electrified by static could create toxic compounds in the soil. Every storm isn't just a threat, it's a clue whispering secrets about how Mars became the desolate world we see today. We've mapped galaxies, counted stars, and even weighed black holes, yet nearly half the universe's expected matter has simply vanished. Not dark matter, which remains its own enigma, but ordinary atoms, the stuff that makes up planets, stars, and us. Scientists call this the missing baryon problem, and it's one of cosmology's most frustrating case files. Based on the echoes of the Big Bang, there should be about twice as much visible matter in the cosmos as we've actually found. So where did it all go? The prime suspects aren't hiding in plain sight, they're lurking in the voids between galaxies, in a form almost impossible to detect, diffuse gas clouds hotter than the sun's core. Imagine a spider web of superheated plasma, stretching millions of light years across cosmic filaments, the scaffolding of the universe. These strands, part of the so-called warm-hot intergalactic medium, or WIM, are so thin and energetic they're practically invisible to traditional telescopes. Gas this hot doesn't emit visible light, it only betrays itself through faint X-ray glows or by bending passing light like a funhouse mirror. Finding this phantom matter took some clever detective work. Astronomers turned to fast radio bursts, cosmic lightning strikes from distant galaxies. As these bursts race across space, they interact with electrons in their path, slowing slightly. By measuring this delay across different wavelengths, researchers could tally the electrons they'd passed, effectively weighing the universe's hidden material. The verdict: a significant chunk of those missing baryons seem woven into these vast, scorching filaments, too spread out to cast shadows but dense enough to tip the cosmic scales. Yet the mystery isn't fully solved. Some of the gas might be even more elusive, trapped in low-density regions too cool to emit X-rays but too warm to absorb light. Others speculate miniature black holes or exotic particles could account for a fraction. What's certain is this: the universe isn't playing hide and seek with its matter out of spite. These baryons are likely the building blocks of future galaxies, the raw material waiting to be recycled in the universe's endless cycle of creation and destruction. They're not lost just patiently biding their time, suspended in the dark threads of the cosmic web. Most stars live quiet lives, tethered to their galaxies by gravity, but not hypervelocity stars. These cosmic fugitives race through space at over 1 million miles per hour, fast enough to escape their home galaxies entirely, destined to drift alone through the void. Take it to be 80,350, a blue giant streaking through intergalactic space at 2.7 million miles per hour, so fast, it could cross the distance from Earth to the Moon in just 6 minutes. This isn't just a star with wanderlust, it's a projectile flung across the cosmos by forces almost beyond comprehension. The culprit: a supermassive black hole's gravitational slingshot. When binary star systems wander too close to a galaxy's central black hole, chaos unfolds. The black hole's immense gravity can rip the pair apart, with one star captured in orbit while the other gets catapulted outward at unimaginable speeds. Picture a cosmic game of crack the whip. As the doomed duo spirals inward, the black hole's tidal forces fling the lighter star away like a pebble from a slingshot, accelerating it to a fraction of light speed in seconds. 80,350 likely endured this violent ejection from the Milky Way's core, making it one of the fastest runaway stars ever discovered. What makes these stars so fascinating isn't just their speed, it's their resilience. Unlike most hypervelocity stars, which eventually slow and fade, 80,350's sheer mass and youth mean it's still shining brilliantly, a beacon visible across intergalactic distances. Its trajectory paints a forensic clue. By tracing its path backward, astronomers pinpointed its origin near Sagittarius A, the Milky Way's central black hole. But here's the twist: it's not alone. Dozens of these rogue stars have been identified, each with velocities defying galactic gravity, each a testament to the violence lurking in seemingly serene galaxies. Yet the real mystery lies in their futures. Unshackled from galactic rotation, these stars won't just drift, they'll outpace the expansion of their home galaxies, crossing into intergalactic space where no new stars form. Over billions of years, they'll cool into stellar corpses, their light fading as they become frozen nomads in the darkness. Some might even collide with other galaxies, seeding them with foreign elements forged in their cores. They're cosmic messages in bottles, carrying the fingerprints of their violent births across the universe. At Saturn's North Pole, a storm rages with a shape so precise, it looks like it was drawn by a cosmic mathematician. Unlike Earth's chaotic hurricanes or Jupiter's swirling storms, this vortex forms a near-perfect hexagon, a six-sided polygon with sides so straight, they defy the turbulence of planetary weather. Stretching 20,000 miles wide, large enough to fit 4 Earths side by side, this eerie structure has persisted for at least 4 decades, possibly longer, spinning in sync with Saturn's rotation as if locked into place by an invisible force. How did a planet known for its graceful rings produce such a rigid geometric tempest? The answer might lie in the physics of spinning fluids. When you stir a cup of coffee, the liquid forms a circular vortex, but Saturn's atmosphere isn't just liquid, it's a deep, layered soup of hydrogen and helium, whipped into motion by the planet's rapid 10-hour rotation. Laboratory experiments suggest that under certain conditions, fast-spinning fluids can stabilize into polygonal shapes, with the hexagon emerging as a balance between rotational speed and atmospheric turbulence. Think of it like a cosmic game of tug-of-war. Saturn's winds shear at different latitudes, but at the pole, these competing forces might synchronize into standing waves, trapping the storm's structure in a stable, hexagonal pattern. But there's another twist. This hexagon isn't just skin deep. Observations from NASA Cassini spacecraft revealed the storm plunges hundreds of miles into Saturn's atmosphere, far deeper than expected. Some scientists argue this points to massive, stacked vortices churning beneath the cloud tops. Think of a series of rotating cylinders, each influencing the layer above, carving the hexagon into the sky like a celestial drill press. Others propose the shape is sculpted by differences in wind speed at various latitudes, creating a phenomenon called Rossby waves, which can trap energy in geometric patterns. Yet the hexagon's most baffling feature isn't its shape, it's its endurance. Earth's weather systems shift by the hour, but Saturn's storm has remained unchanged across multiple spacecraft missions. This stability hints at something fundamental about gas giants. Their lack of solid surfaces means atmospheric patterns can persist for centuries, undisturbed by mountains or oceans. The hexagon might even be a window into Saturn's hidden depths, where rotation and convection conspire to create order from chaos. One thing's certain, this isn't just a curiosity. Similar hexagonal patterns have been spotted at Saturn's south pole, though less defined, suggesting the phenomenon might be a universal quirk of rapidly rotating planets. For future missions, unlocking the hexagon's secrets could reveal how energy moves through gas giants, and whether such geometric storms might lurk in the atmospheres of exoplanets light years away. For now, it stands as a reminder that nature doesn't just favor chaos. Sometimes it drafts perfect shapes in the sky, just to keep us guessing. Time doesn't just pass the same way everywhere in the universe. Near a black hole, it warps and twists like rubber stretched to its limit. Remember Interstellar's Gargantua, where every hour on the water planet meant 7 years back on the ship? That wasn't just Hollywood drama. It's real science, a mind-bending effect called gravitational time dilation, predicted by Einstein's theory of relativity. The closer you get to an object with immense gravity like a black hole, the slower time crawls compared to somewhere far away. Picture two identical clocks, one placed near Earth's surface, the other drifting in empty space. Over time, the clock in Earth's gravity would tick slightly slower, lagging behind its space-bound twin by microseconds. Now crank that up to black hole levels, where gravity isn't just strong, it's space-time itself collapsing. Here's how it works. Massive objects like black holes dent the fabric of space-time like a bowling ball sinking into a trampoline. The steeper the dent, the harder time has to climb out, slowing to a near standstill near the event horizon. To an outside observer, someone falling into a black hole would appear frozen in time, their movement stretching into infinity, but for the doomed astronaut, time would feel normal right up until the moment spaghettification kicked in. This isn't just theoretical. GPS satellites orbiting Earth have to account for time dilation, adjusting their clocks because they experience weaker gravity than we do on the ground. Without these corrections, your navigation apps would misplace you by miles within minutes. The real kicker, time dilation isn't a one-way street. If you could orbit just outside a black hole's lethal grip, close enough to feel its pull but far enough to escape, you'd return to a universe that aged centuries without you. You become a time traveler, leaping into the future with every loop. It's a paradox that reshapes our understanding of reality. Gravity doesn't just bend light or trap matter. It molds time itself, turning the cosmos into a labyrinth where past, present, and future are anything but absolute. And while we'll never surf the edge of a black hole, their existence proves something profound: time isn't universal. It's as fluid as a river, flowing at different speeds across the stars. the Moon doesn't just orbit Earth in a steady, predictable loop. It wobbles. Over an 18.6-year cycle, its gravitational pull subtly shifts, tilting our planet like a spinning top, losing balance. For most of this cycle, the effects are mild, barely noticeable, but when this wobble aligns with rising sea levels, something alarming happens. Coastal cities worldwide face a flooding crisis unlike anything in recorded history. NASA scientists warn that by 2030, this lunar wobble will combine with climate-driven sea level rise to unleash a perfect storm of high tides, pushing floods from rare emergencies into monthly nightmares. Here's how it works. The Moon's gravity tugs on Earth's oceans, creating the tides we see every day, but that pull isn't uniform. It fluctuates based on the Moon's position in its orbit. During the amplification phase of the wobble, the Moon's angle intensifies high tides while suppressing low ones, effectively stacking water along coastlines. Normally, this wouldn't be catastrophic, yet with sea levels already creeping upward due to melting ice and warming seawater, even a minor tidal boost becomes dangerous. Think of it like a bathtub filling slowly, then someone bumps the faucet, sending water sloshing over the edge. The consequences are staggering. Cities like Miami, Mumbai, and Bangkok, already battling routine flooding, could see their defenses overwhelmed as high tides surge an extra foot or more. What were once 100-year floods might strike every few weeks, crippling infrastructure, contaminating freshwater supplies, and displacing millions. And it's not just storms causing the damage. This is silent, sunny day flooding, where water bubbles up from storm drains with no warning, turning streets into rivers. But why now? Historical data shows the wobble has existed for millennia, but never before has it coincided with such rapidly rising seas. In the past, natural variability balanced the effects. Today, climate change acts as a force multiplier, turning a minor orbital quirk into a humanitarian threat. The last time this phase peaked in the mid-2030s, satellites didn't exist to monitor it. This time we're watching in real time, and the forecasts are grim. The silver lining: foreknowledge is power. By understanding this cycle, cities can accelerate seawall projects, redesign drainage systems, and relocate critical infrastructure. The wobble itself can't be stopped, but its worst impacts can be blunted. Still, it's a haunting reminder: even celestial rhythms we've long taken for granted can become hazards when paired with Earth's changing climate. The Moon isn't just our neighbor in space, it's a silent player in our planetary future, nudging the tides toward a crisis we can still prepare for if we act fast. Mercury seems like the last place you'd find ice, a scorched world where daytime temperatures soar to 430 degrees Celsius, hot enough to melt lead. Yet hidden in the planet's polar craters where sunlight never reaches, lie vast deposits of water ice, some as thick as 50 meters. This discovery, confirmed by NASA Messenger mission, flipped planetary science on its head, proving that even the most hellish environments can harbor frozen water if conditions are just right. The secret lies in Mercury's extreme tilt, or lack of it. Unlike Earth, which wobbles on its axis, Mercury rotates almost perfectly upright. This means its poles never tilt toward the sun, leaving deep craters in permanent shadow. These sunless pits become natural freezers, with temperatures plunging to -170 degrees Celsius, cold enough to preserve ice for billions of years. But here's the puzzle: where did the water come from? The leading theory points to comet impacts. Over eons, icy comets smashing into Mercury could have delivered water vapor, which migrated to the poles and froze in these frigid traps. Another possibility involves solar wind, charged particles from the sun that carry hydrogen, which might bond with oxygen in Mercury's rocks to form water molecules. Messenger evidence was unmistakable. Using neutron spectroscopy, the probe detected telltale signatures of hydrogen, a key component of water, concentrated in the polar regions. Radar images from Earth had hinted at reflective patches decades earlier, but Messenger proved they weren't just oddly textured rock. some craters, like the sprawling Prokofiev Basin, contain enough ice to bury Manhattan under a layer 10 stories deep. This ice isn't just a scientific curiosity, it's a game changer. If Mercury, a planet practically kissing the Sun, can hoard water, then ice might lurk in unexpected places across the solar system. Future lunar or Martian colonists could use similar shadowed craters as natural ice mines, harvesting water for drinking, farming, or even rocket fuel. And for planetary scientists, Mercury's ice is a time capsule, preserving clues about how water, the essential ingredient for life, hitchhiked across the cosmos. The twist: some of Mercury's ice is coated in a mysterious dark material, possibly organic compounds. This raises even wilder questions. Could comets have sprinkled the seeds of life on the solar system's inner planets? While Mercury itself is too hostile for life, its ice tells a story of cosmic delivery, proving that water, and maybe the building blocks of biology, are far more mobile than we ever imagined. Olympus Mons isn't just the tallest volcano in our solar system, it's a behemoth that makes Earth's mightiest mountains look like foothills. Towering 16 miles high, this Martian giant stands nearly 3 times taller than Mount Everest, with a base so wide it could swallow the entire state of Arizona. But what's truly mind-blowing isn't just its size, it's how Mars's unique geology allowed this monster to grow so unimaginably large. Unlike Earth, where tectonic plates constantly shift and recycle the crust, Mars is a static world, its surface frozen in place for billions of years. That stability, paired with the planet's feeble gravity, created the perfect recipe for volcanic titans. On Earth, volcanoes like Hawaii's Mauna Loa erupt, spew lava, and eventually drift away from their magma sources as tectonic plates move. But on Mars, the crust stays put, letting magma rise through the same vents over eons, piling layer upon layer of solidified lava into a single, staggering peak. With gravity only 38% as strong as Earth's, Martian volcanoes can grow taller without collapsing under their own weight. Picture building a sandcastle. On Earth, it crumbles once it gets too steep, but on Mars, the weaker gravity lets you stack it twice as high before it topples. That's why Olympus Mons doesn't just scrape the sky, it dominates it. With slopes so gently inclined you could hike them without realizing you're climbing a mountain, until the thin air and sheer scale leave you breathless. Yet the volcano's most surprising feature might be its youth. While Mars's volcanic heyday ended hundreds of millions of years ago, some studies suggest Olympus Mons could still be geologically active, with magma simmering deep underground. Recent satellite images even reveal faint thermal signatures and fresh lava flows, clues that this colossus might not be entirely extinct. Imagine standing on its summit, gazing across a caldera 50 miles wide, knowing the ground beneath you might still hold molten rock, waiting for the next eruption. What does this mean for the red planet's history? Olympus Mons is a time capsule, preserving evidence of a time when Mars bubbled with volcanic fury, its atmosphere thick enough to support rivers and maybe even life. Today it stands as a monument to planetary extremes, proof that without plate tectonics and with a gentle gravitational touch, nature can sculpt mountains that dwarf anything in our terrestrial imagination. And for future explorers, it's more than a landmark, it's a challenge, a summit waiting to be conquered, on a world where the mountains don't play by Earth's rules. Stepping back into the airlock after a spacewalk, astronauts report something utterly unexpected. Space has a smell, not the sterile nothingness you'd imagine, but a pungent, almost grotesque aroma clinging to their suits, a mix of seared steak, hot metal, and gunpowder. This isn't space madness, it's a quirk of chemistry that reveals the universe's hidden flavors. When astronauts remove their helmets, the scent hits them immediately, a lingering metallic tang mixed with charred organic notes, as if the vacuum itself had been grilling particles onto their gear. So where does this cosmic barbecue smell come from? The leading theory points to polycyclic aromatic hydrocarbons, or complex molecules forged in the fires of dying stars. These carbon-rich compounds float through space, sticking to astronaut suits during exposure to the vacuum. When they repressurize the airlock, oxygen reacts with these stardust residues, creating volatile compounds that mimic the smell of burnt meat. It's like opening an oven door after roasting, except the oven is the void between stars, and the roast is the leftover remnants of stellar explosions. But there's another twist: the smell might also come from atomic oxygen. In low Earth orbit, single oxygen atoms, not the paired O2 we breathe, cling to spacesuits, corroding metal and interacting with organic materials to create that acrid, metallic edge. The result? A scent that's equal parts welding shop and steakhouse, a bizarre olfactory signature of humanity brushing against the cosmos. This isn't just a quirky anecdote, it's a clue to the universe's chemical complexity. Those same hydrocarbons that stick to spacesuits are the building blocks of life, scattered across galaxies by supernova and comet impacts. Every time an astronaut catches a whiff of that post-spacewalk aroma, they're literally smelling the ingredients of creation, the same particles that might have seeded Earth's primordial soup billions of years ago. The irony is delicious. The vast, airless void we think of as scentless is actually a reservoir of potent odors, preserved in pristine form until humans bring them inside. Future Mars travelers might encounter entirely new cosmic smells, perhaps the rusty tang of iron oxide drifting from the red planet's dust, or the sulfuric punch of volcanic residues. One thing's certain: space isn't just a visual spectacle, it's a full sensory experience waiting to surprise us at every turn. The sun isn't just a silent ball of fire, it rings like a colossal bell, vibrating with deep, resonant waves that reveal its hidden secrets. Scientists call this field of study heliosismology, and it works like cosmic echolocation, decoding the sun's inner structure by listening to its oscillations. Imagine tapping a giant gong and hearing echoes that tell you not just its shape, but what it's made of, layer by layer. That's exactly what happens with our star, except the taps come from turbulent convection deep in its core, where gas churns like a boiling pot, sending pressure waves rippling outward in a symphony of solar sound. These aren't audible vibrations, they're pressure waves trapped inside the sun, bouncing between its surface and core in cycles that can last minutes or hours. Some race across the solar surface like ripples on a pond, while others plunge straight through the sun's heart, bending as they pass through dense layers. By measuring these waves with space-based observatories like NASA's Solar Dynamics Observatory, scientists create detailed maps of the sun's interior, much like doctors use ultrasound to image a patient's organs. The data reveals everything from rotation speeds to temperature variations, exposing dynamic currents and even the birthplace of sunspots before they erupt onto the surface. What's astonishing is how precise these solar echoes are. Just as a cracked bell rings off key, deviations in the sun's vibrations betray hidden anomalies. In the 1990s, heliosismology solved a decades-old mystery: why detectors on Earth kept missing the predicted number of neutrinos streaming from the sun. The waves showed that the sun's core was as hot as theories suggested, proving neutrinos weren't missing, they were simply changing form en route to Earth. This discovery upended particle physics and earned a Nobel Prize, but the sun's music isn't just for science, it's a warning system. Changes in its acoustic patterns can signal looming solar storms, giving us crucial days to shield satellites and power grids. And here's the cosmic twist: stars across the galaxy likely sing similar songs. By mastering heliosismology, we're learning to eavesdrop on distant suns, decoding their ages, compositions, and even potential habitable zones from their stellar vibrations. The universe, it turns out, isn't just a silent void, it's a concert hall, with stars as its instruments and physics as the conductor. Earth doesn't just have one moon, it has a secret second companion, a cosmic hitchhiker named Kama'olwa, dancing around us in a celestial game of tag. Discovered in 2016, this asteroid, no bigger than a Ferris wheel, orbits the Sun in such perfect sync with Earth that it appears to circle our planet like a tiny moon. But don't expect it to stick around forever. Kamolwa is what astronomers call a quasi-moon, a temporary tag-along with a bizarre, horseshoe-shaped orbit that keeps it close to Earth for decades before the Sun's gravity inevitably steals it back. What makes this space rock so special isn't just its path, it's the precision of its dance. Most asteroids zip past Earth in erratic ellipses, but Kamolwa moves in a graceful loop, spending about half its time leading Earth around the Sun and the other half following us, like a cosmic shadow. This happens because its orbital period, the time it takes to circle the Sun, is nearly identical to Earth's, differing by just a few days. The result: a gravitational waltz where Earth gently nudges the asteroid back and forth between inner and outer orbits, creating that distinctive horseshoe shape when traced over centuries. But here's the twist: Kamolwa isn't alone. Earth has hosted dozens of these transient moons over its history, each lingering for a few decades or centuries before drifting away. Some, like the asteroid 2006 RH120, even switch between being quasi-moons and temporary captured satellites, looping around Earth in chaotic spirals before breaking free. These objects aren't bound by gravity like our moon, they're just passing through, trapped in a gravitational eddy created by the tug-of-war between Earth and the Sun. And then there's the mystery of Kamolwa's origins. Spectroscopy suggests its surface resembles lunar rock, sparking wild theories. Could it be a chunk of the moon, blasted into space by an ancient impact? Or perhaps a fragment of a larger asteroid that once brushed too close to Earth? Future missions like China's planned Tianwen-2 probe aim to visit Kamolwa, scoop up samples, and finally answer these questions. For now, this mini-moon is a reminder that Earth's gravitational reach extends far beyond the moon. Our planet doesn't just travel solo, it's constantly surrounded by a cloud of transient companions, some lasting lifetimes, others mere years. And while Kamolwa will eventually leave our cosmic neighborhood, its presence hints at a dynamic solar system where even the smallest objects can find fleeting harmony with giants like Earth. Our galaxy isn't just a serene island of stars, it's a cosmic predator, slowly devouring its smaller neighbor in an act of galactic cannibalism that's been unfolding for billions of years. The victim, the Canis Major dwarf galaxy, a tiny satellite galaxy currently being torn apart by the Milky Way's immense gravity, its stars strewn across space like crumbs from a celestial feast. This isn't a violent collision but a gradual disintegration, a process so slow it makes continental drift seem lightning fast, yet the evidence is everywhere if you know where to look. The telltale sign lies in the Monoceros ring, a vast looping stream of stars wrapping around the Milky Way's disk like a celestial serpent. This ribbon of starlight, discovered in 2002, isn't part of our galaxy's original structure. It's the shredded remnants of Canis Major, its stars ripped away by tidal forces as the dwarf galaxy orbits too close to the Milky Way's gravitational jaws. Picture a sponge being squeezed. As Canis Major passes through our galaxy's dense halo, stars near its edges get pulled outward, forming long tendrils that trace its doomed path. These tidal streams aren't just debris, they're a forensic snapshot of destruction in progress, revealing how galaxies grow by consuming their smaller kin. What makes this feast so fascinating is its scale. Canis Major was never a giant, it's one of the Milky Way's faintest known companions, with just 1 billion stars compared to our galaxy's hundreds of billions. Yet its demise has left an indelible mark. Infrared telescopes which peer through obscuring dust show the dwarf galaxy's core still clinging together, a dense knot of stars and dark matter being stripped layer by layer. Meanwhile, its shredded outer regions have already blended into the Milky Way's halo, their stars joining the swirling pool of material that might one day form new generations of suns and planets. This process isn't unique. Galactic cannibalism is how all large galaxies grow. The Milky Way has absorbed dozens of smaller galaxies over its lifetime, with Canis Major merely the latest course in its cosmic meal. Even our galaxy's iconic spiral arms might owe their shape to past mergers, their structures stirred by the gravitational wake of devoured dwarfs, and the feast isn't over. The neighboring Large Magellanic Cloud is next in line, destined to be torn apart in about 2.5 billion years. Yet Canis Major's destruction holds a special irony. Its stars, now scattered across the Milky Way, are older and richer in heavy metals than many of our galaxy's native stars, suggesting it was once a prolific star-forming region. In devouring its neighbor, the Milky Way isn't just growing, it's inheriting a treasure trove of ancient stellar chemistry, remnants of a galaxy that thrived long before Earth existed. It's a humbling thought. Even the stars above us aren't all native to this galactic shore. Some are cosmic immigrants, their origins lost to time, their stories written in the slow, silent dance of gravity and time. The universe teems with billions of potentially habitable planets, so as it feel like we're utterly alone, the silence isn't just puzzling, it's terrifying, and one explanation paints a picture of cosmic survival so ruthless, it redefines what it means to be intelligent. Meet the dark forest theory, a chilling answer to the Fermi paradox that suggests alien civilizations aren't just rare, they're hiding, deliberately mute to avoid attracting the attention of something far worse. Popularized by Liu Cixin's Remembrance of Earth's Past trilogy, this idea frames the cosmos as a lawless wilderness where every hunter stays silent, fearing that any signal, any footprint, could mark them for extermination. Think of it like this. Imagine you're lost in a dark forest at night, where every rustle could be a predator. Do you shout to find friends, or stay quiet to stay alive? The theory argues that advanced civilizations face the same dilemma. Broadcasting your location might invite not curiosity, but annihilation. After all, any species capable of interstellar travel could also possess planet-killing technology, and in a universe where resources are finite, preemptive strikes might be the only rational strategy. It's not paranoia if the alternative is extinction. This isn't just sci-fi speculation. The debate has real stakes for projects like SETI, which actively searches for alien signals. Some scientists argue that sending messages into the void, like the famous Arecibo transmission, is reckless, akin to lighting a bonfire in that dark forest. Others counter that hiding is equally risky. A civilization advanced enough to detect our radio leaks might already know we're here. The truth could lie in between. Perhaps the galaxy is dotted with civilizations, all listening, none daring to speak first, locked in a stalemate of silence. What makes the dark forest so unsettling isn't just its pessimism, it's its plausibility. Evolutionary biology shows that life often competes ruthlessly for survival, and human history is littered with cultures destroyed by more aggressive neighbors. If the same logic applies cosmically, the Great Silence isn't a mystery, it's a warning. Until we know who or what might be listening, our safest bet might be to tread quietly, leaving no trace in the dark. While most planets spin like tops as they orbit the Sun, Uranus performs a cosmic cartwheel, rolling around its star like a barrel flung sideways. With its axis tilted a staggering 98 degrees, this ice giant doesn't just lean slightly, it's practically lying down, making it the solar system's ultimate oddball. Unlike Earth's gentle 23-degree tilt, which gives us predictable seasons, Uranus's extreme posture means its poles take turns pointing directly at the Sun for decades at a time, plunging half the planet into endless daylight while the other half freezes in perpetual night. The leading theory behind this bizarre orientation involves a cataclysmic collision early in the solar system's history. Picture a rogue planet, perhaps twice Earth's size, slamming into Uranus with such force that it knocked the giant clean off its original axis. The impact wouldn't just have changed its tilt, it might have also superheated the planet's core, explaining why Uranus, unlike its sibling Neptune, radiates almost no internal heat today. Some models suggest the collision could have even vaporized part of Uranus's icy mantle, leaving behind a lopsided distribution of material that still affects its gravitational field. This sideways spin creates seasons unlike anything else in our solar system. For 21 Earth years, one pole basks in uninterrupted sunlight, while the opposite pole endures a frigid, pitch-black winter. Then, as Uranus completes its 84-year orbit, the roles reverse. The transition between seasons triggers monstrous storms, with winds howling at 560 miles per hour, fast enough to rip apart Earth's sturdiest structures. Even stranger, during equinox, when the sun shines directly over Uranus's equator, the planet's rings briefly appear edge-on, casting shadows so precise they act like a cosmic sundial. Yet the tilt might explain another mystery: Uranus's oddly quiet magnetic field, which wobbles off-center and doesn't align with its rotational axis at all. Most planets generate magnetic fields from molten metal cores, but Uranus's field seems to arise from slushy, electrically conductive water and ammonia deeper in its interior. The impact that knocked it sideways could have scrambled these layers, creating a magnetic field as chaotic as its seasons. For future explorers, Uranus presents a world of extremes. Landing near its North Pole during summer would mean experiencing a sun that never sets, circling the sky in a tight spiral for years. Meanwhile, the South Pole would remain a frozen wasteland, untouched by sunlight for generations. This isn't just a planet with odd weather, it's a laboratory for how celestial violence shapes worlds, proving that in the cosmic pinball machine of the early solar system, even giants could be knocked flat. The universe is expanding, that much we know, but how fast? That simple question has cosmologists locked in one of the most heated debates in modern science, a full-blown crisis called the Hubble tension. On one side, we have meticulous measurements of the cosmic microwave background, the afterglow of the Big Bang, pointing to an expansion rate of about 67 kilometers per second per megaparsec. On the other, observations of supernovae in nearby galaxies suggest the universe is sprinting outward at 73. That 6-kilometer gap might sound trivial, but it's the difference between a rounding error and a revolution, because both numbers can't be right, and the discrepancy might mean we're missing something fundamental about how the cosmos works. Let's break this down. The cosmic microwave background, or CMB, acts like a baby picture of the universe, frozen in time just 380,000 years after the Big Bang. By studying its subtle temperature variations with missions like Planck, scientists can extrapolate how fast space should be stretching today. It's like calculating how tall a child will be as an adult based on their height at age 2. Supernova, though, give us a direct snapshot of the present. These exploding stars serve as standard candles, objects with known brightness, letting us gauge distances across space. When their observed brightness doesn't match predictions, it reveals how much the universe has expanded since their light left them. Both methods are painstakingly precise, yet they stubbornly refuse to agree. This isn't just academic quibbling. If the supernova measurements are correct, it implies the universe's expansion is accelerating faster than our models predict, possibly due to an unknown form of dark energy or even modifications to Einstein's gravity. Some theorists speculate there might have been a brief burst of hyper-expansion early in cosmic history, imprinting extra speed that the CMB doesn't account for. Others wonder if we're seeing hints of exotic particles or hidden dimensions tweaking the fabric of reality. The wildest possibility, we're witnessing the first cracks in our understanding of physics itself, a sign that the rules we've relied on for a century need rewriting. The stakes couldn't be higher. If the Hubble tension holds, it could upend cosmology, forcing us to rethink everything from the age of the universe to its ultimate fate. Will it end in a cold, empty whisper, or rip apart in a big rip? Right now, we can't say for sure because the universe, it seems, is keeping two sets of books. And until we solve this puzzle, every answer comes with an asterisk. Imagine a star that refuses to die exploding in a catastrophic supernova, only to cling to life and reignite like a cosmic phoenix. These aren't just survivors, they're stellar zombies, defying the very definition of death. Type Ia supernova were long thought to be the final act for white dwarf stars, detonating so completely that nothing remained. But in 2012, astronomers got a shock when they spotted a white dwarf named Tycho G, lurking in the remnants of Tycho's supernova, a star that had supposedly blown itself to smithereens 450 years earlier. Somehow, this celestial ghost had endured one of the most violent events in the universe and lived to tell the tale. The secret lies in how these supernovae detonate. Most Type Ia explosions occur when a white dwarf, the dense core of a dead star, siphons too much material from a companion star, pushing it past a critical mass limit. The result is a thermonuclear chain reaction that tears the dwarf apart in seconds, but Tycho G suggests some white dwarfs might survive by ejecting just enough material during the blast to avoid total annihilation. Picture a bomb going off in a star's core, but instead of disintegrating, it's kicked clear of the worst destruction, left scorched but intact, a charred ember drifting through its own funeral pyre. The implications are staggering. If white dwarfs can cheat death, it means our models of supernova need rewiring. These zombie stars could explain why some supernova remnants appear lopsided or lack expected debris patterns. Their surviving cores might have altered the explosion's shape. Tycho's remnant itself is a puzzle. Its shockwaves form an uneven bubble, with Tycho G drifting off-center like a bullet that ricocheted mid-blast. This could mean the dwarf was sent careening by the explosion's force, a celestial cue ball knocked askew by its own detonation. But here's where it gets even stranger. Some of these undead stars don't just limp away, they reignite. In 2018, astronomers watched as a white dwarf named LP 40-145 flared back to life years after its supernova, glowing with renewed heat as if fed by some hidden energy source. The leading theory: these stars might retain a sliver of unstable fuel just enough to spark secondary fusion reactions, turning them into ticking time bombs that could explode again. What does this mean for the cosmos? Zombie stars challenge our understanding of stellar life cycles, proving that even in death, stars have tricks up their sleeves. They might be rare, but their existence hints at a universe where the line between dead and alive is blurrier than we thought. And for astronomers, they're a goldmine, cosmic Rosetta stones that could decode how supernova seed galaxies with the heavy elements that build planets, life, and even us. After all, if a star can rise from its own ashes, what other cosmic rules are waiting to be broken? The moon might seem like a dead, unchanging rock, but its dusty surface hides the ghost of a long-lost power traces of an ancient magnetic field locked inside lunar rocks. Unlike Earth, where our protective magnetic shield hums steadily thanks to a churning molten core, the moon today is a barren wasteland, its magnetic field long extinguished. Yet samples brought back by Apollo astronauts tell a different story. Tiny mineral crystals aligned like compass needles, frozen in time, proving that billions of years ago, our celestial neighbor crackled with a magnetic force strong enough to rival Earth's. How did a world just 1% of Earth's mass muster such a magnetic powerhouse? The answer lies deep beneath the lunar surface. In its youth, the moon likely harbored a molten iron core, swirling with convective currents that acted like a dynamo. As this liquid metal sloshed and spun, it generated a magnetic field the same way Earth's core does today, but with a twist. The moon's smaller size meant its core cooled rapidly, losing heat to space far faster than our planet. Within a billion years, temperatures plummeted, the core solidified, and the dynamo sputtered out, leaving behind only magnetized rocks as tombstones to its former glory. Here's where the mystery deepens. Some lunar samples suggest the moon's magnetic field didn't fade gently, it flickered erratically, surging in strength before vanishing entirely. One theory blames massive asteroid impacts. When a city-sized rock slammed into the moon, the collision could have jolted the core like a spoon stirring a pot, temporarily reigniting the dynamo. Another idea points to a slow, uneven cooling process, where pockets of molten metal lingered, creating localized magnetic zones long after the global field collapsed. The implications stretch far beyond lunar geology. If a small body like the Moon once had a robust magnetic field, other moons and dwarf planets in our solar system or even exoplanets might have hosted similar shields, guarding their surfaces from deadly solar radiation. That's a game changer for the search for life, as magnetic fields are crucial for protecting atmospheres and liquid water. The Moon's magnetic ghost whispers a tantalizing possibility. Even the most unassuming worlds might have once throbbed with unseen energy, their stories locked in stone, waiting for us to listen. For every star twinkling in our galaxy, there could be a hidden world drifting alone in the abyss, a rogue planet, untethered from any solar system, condemned to wander the eternal night. A 2020 study from Ohio State University estimated there might be 50 billion of these cosmic nomads lurking in the Milky Way, far outnumbering the stars themselves. Picture Earth ripped from the sun's warmth, floating through interstellar space where temperatures hover near absolute zero, its oceans frozen solid beneath an atmosphere that's collapsed into icy rain. That's the reality for these orphan worlds, some larger than Jupiter, others rocky like Mars, all banished from their birthplaces by gravitational chaos or stellar violence. The most chilling part, we've barely begun finding them. Unlike planets orbiting stars, which betray their presence through telltale dimming or wobbles, rogue planets are nearly invisible. They don't reflect sunlight or cast shadows. To spot them, astronomers rely on a phenomenon called microlensing. When one of these dark wanderers passes in front of a distant star, its gravity bends the starlight like a lens, creating a brief flash in the void. That's how we've confirmed a handful, like the free-floating OFF-33, a Jupiter-sized outcast drifting 400 light-years away. But microlensing is a cosmic game of chance, like catching a single firefly blinking in a pitch-black stadium. Where do all these lost worlds come from? Some are ejected from their fledgling solar systems by gravitational tugs of war, flung into the abyss like stones from a slingshot when gas giants jockey for position. Others might form directly from collapsing gas clouds, miniature failed stars never dense enough to ignite fusion. The darkest possibility, many could be graveyard planets, survivors of dead solar systems, their stars long burned out, leaving them to orbit nothingness. Yet rogue planets aren't just cosmic tragedies. In their frozen hearts they might harbor secrets and even life. Tidal heating from a moon, or radioactive decay deep underground, could keep subsurface oceans liquid for billions of years. Imagine extremophile microbes thriving in pitch-black seas beneath miles of ice, oblivious to the fact their world orbits no sun. These planets might be the ultimate ark ships, carrying the potential for life between the stars, seeding it wherever they eventually collide with a new solar system. The scale of their loneliness is hard to fathom. While stars cluster in galaxies and planets huddle around their suns, rogue worlds sail through the void at hundreds of thousands of miles per hour, their nights unbroken by sunrise, their skies devoid of constellations. Yet they're not truly alone. Billions of their kind share the darkness, a shadow population of worlds we're only now learning to see. And if life can cling to existence on these frozen outcasts, the galaxy might be far stranger and far more crowded than we ever dared to dream. Every story has an ending, and the universe is no exception, but its finale won't be a dramatic explosion or a fiery collapse. Instead, scientists predict a slow, silent fade into darkness, a fate known as heat death. This isn't just poetic gloom, it's the inevitable consequence of entropy, the universal law that says disorder always increases, picture a cup of hot coffee left on the counter. No matter how long you wait, it'll never spontaneously heat up again. The universe works the same way. Over trillions of years, all usable energy will spread thin, stars will burn out, and even black holes will evaporate, leaving behind a vast, lifeless sea of particles too far apart to interact. The cosmos won't end with a bang, but with a whisper, a state so cold and empty, time itself may lose all meaning. For decades, the heat-death scenario has been the leading theory, but it wasn't always the only contender. Some cosmologists once favored the Big Crunch, a mirror image of the Big Bang where gravity would reverse the universe's expansion, pulling everything back into a singularity. The appeal was symmetry, a cyclical universe that breathed in and out like cosmic lungs, but observations in the late 1990s shattered that idea. Astronomers studying distant supernovae discovered the universe wasn't just expanding, it was accelerating, propelled by an invisible force we now call dark energy. This revelation tipped the scales. If expansion has no brakes, gravity can't win. The Big Crunch is off the table, and heat death is the frontrunner by a landslide. What makes heat death so unnerving is its utter finality. Unlike fiery apocalypses or black hole collisions, this isn't a singular event, it's a process, playing out over timescales so vast they dwarf human comprehension. First, galaxies will drift apart until their light can no longer reach one another, leaving each island of stars alone in an ever-darkening sky. Next, star formation will sputter out as gas clouds thin beyond recovery, and existing stars will exhaust their fuel, collapsing into faint remnants like white dwarfs and neutron stars. Even these will eventually decay, their protons dissolving over unimaginable eons until only photons and black holes remain, and in the end, those black holes will emit Hawking radiation, leaking mass until they too vanish, leaving behind a void where nothing happens forever. Yet there's a strange beauty in this cosmic finale. Heat death isn't destruction, it's transformation, the universe settling into its lowest possible energy state, like a clock winding down. Some theorists even speculate about quantum fluctuations sparking new big bangs in the emptiness, birthing fresh universes in the ashes of our own. But for now, the evidence points to a colder truth. The universe is on a one-way trip toward equilibrium, where every difference, hot and cold, light and dark, smooths out into perfect, endless sameness. It's a humbling thought. All our struggles, our art, our civilizations, even the stars themselves, are just temporary eddies in a river flowing inexorably toward stillness. The universe doesn't end with fire or ice, but with the ultimate silence, a sea of darkness where even time forgets to move. From a moon that's slowly abandoning Earth to a galaxy tearing apart its neighbor, we've journeyed through cosmic truths so bizarre, they rewrite reality as we know it. Space isn't just vast, it's a realm where planets rain glass, stars scream in silence, and entire oceans of water float near black holes older than time itself. Each discovery peels back another layer of the universe's endless contradictions, proving that the cosmos thrives on defying our expectations. Whether it's the hexagon storm on Saturn or zombie stars that cheat death, these aren't just curiosities, they're humbling reminders that human knowledge is a tiny island in an ocean of mysteries. Think about it, we've mapped the human genome and split the atom, yet we're still unraveling why Uranus rolls like a barrel, or how half the universe's matter vanished without a trace. The deeper we dig, the more the universe throws back questions we never thought to ask. That's the beauty of space. It doesn't just surprise us, it shatters our assumptions, forcing us to rethink the very laws of physics. And with every answer, a dozen new enigmas emerge, from rogue planets adrift in the dark to the eerie silence that might hide civilizations too afraid to speak. So here's the real challenge: which fact left you utterly breathless? Was it the great attractor's invisible pull, dragging galaxies toward an unknown fate? Or the chilling dark forest theory, suggesting the cosmos might be a battlefield of silent predators? Drop your thoughts below, we're all cosmic detectives here, piecing together the universe's greatest puzzles. And if these mysteries lit up your curiosity like a supernova, don't miss out on the next mind-bending revelation. Hit subscribe because the universe is far from done shocking us. The next discovery, it's lurking out there, waiting to blow your mind all over.